Okay. I do want to encourage you to attend discussion section as well. I know I know it's like not at the best times. It's like 8 a.m., right? 8 a.m., 9 a.m., 5 p.m. Are you guys the 5 and 6 p.m. or the 8 a.m., 9 a.m.? You guys are, okay, all right. Well, I mean, if you prefer to do 8 a.m. and 9 a.m., that's also fine, okay? That's for lecture 1. You know, the thing about scheduling all your classes in the morning is you're like done by noon, and you do whatever you want, right? So, all right. But anyway, I want to talk about setups and shortcuts and stuff when you're doing stuff on the computer with RStudio and whatnot. I am a big fan of RStudio as far as using it for interacting with R and data and things like that. I think it's truly a great interface. You know, if the job is software engineering and you're trying to create, write a program and script and things like that, yeah, sure. Other tools might be better suited, VS Code and stuff like that. But as far as interacting with data, I really think it's hard to beat RStudio. Now, one tip, and I strongly encourage this, is create a folder for each homework assignment. Okay, so your first homework assignment, homework 1, make a folder, homework 1. Okay, make a folder for homework 2, make a folder for homework 3. Okay, and then download your files, relevant files, put them all into homework 1. Okay, download the relevant files, put them into homework 2 and stuff. So for this first homework assignment, you're going to download the PDF instructions. You'll download the RMD file. There's also a text file with month names, and you'll put that all in the same homework file folder. Okay, you'll also have to create a script, your script.r. You'll also put that in the homework folder. Okay. One thing that always kind of kills me a little bit is, a student comes and says, hey, I need some help during office hours. That part doesn't kill me. I'm very happy for you to come by office hours to ask for help. But then I say, okay, well, let's open up your thing. And then it's like they're opened straight from their downloads folder, right? And the downloads folder is just full of like everything from the, the beginning of the computer. So it's like full of like random photos and programs and attachments and PDFs and all sorts of different stuff, and it's just a huge kind of mess in there. And yeah, you know what? R is going to have a hard time just kind of keeping track of it. It's not that it has to keep track of everything, but it's very easy for things to get kind of mixed up if you just have everything in just one giant folder there. So set up different directories. Another tip is sometime in the future, you might have to use the command line, and your life will be much easier if you don't have spaces in your folder names. So use underscores or dashes instead of spaces in your folder names, in case you ever have to use the command line, which could be a thing. Once you have the stuff in your folder and you open it up, one thing that you should do is you should set your working directory, okay? And this tells R, while I'm working on this thing, whenever you look for stuff, start here, start in the working directory, okay? So you just go to from the menu, you go to session, set working directory to source file location, and it will set it to the folder from where you opened the thing, right? So if you've downloaded your stuff into homework 1, the folder homework 1, and you open up the homework 1 file and you say set working directory to source file location, it's going to set that homework 1 folder as the working directory. Okay, and then whenever it looks for stuff, it's going to look for there. This is a common error that students encounter. You get something, cannot open file, month names.txt, no such file or directory, error in file rt, cannot open the connection. Okay, and basically what this is saying is R is searching for this file, monthnames.txt, and it searches for it in the working directory and it doesn't find it, right? And either one of two things is going on here, okay? Maybe you have the working directory set correctly to your homework 1 folder, and monthnames.txt you didn't save it in that folder, okay? Or another thing that could be going on is you have month names saved in your homework 1 folder, but then you didn't set your working directory. So R is searching your downloads folder or something like that, and it's looking in there and it's not finding monthnames.txt. So, you know, fix the problem, right? Either put the file in the folder or you set your working directory. This should solve a lot of the issues here. Okay. Now, don't hesitate to go on CampusWire. You encounter an error. Okay. Don't hesitate to like screenshot that error message and post it on CampusWire and say, hey, what can you help me figure out what's going on? That's fine. I do ask that you don't post all of the code that you've written that produces the error message. Okay. A lot of times you can try to figure out what's going on without having to paste all of your code. Okay. Another thing is that I strongly recommend regularly checking and clearing the environment. Okay. So as you work, your environment or your workspace fills up with objects. Okay. And this all shows up in kind of the environments pane on RStudio. So this area up here is your environment pane, and I recommend just clicking this little broom icon and just deleting everything out, okay? And you'll have an empty environment, okay? Oops. And that's kind of a good habit. Anytime you start a new project, anytime, even like as you start like a new problem inside your homework, it's probably a good idea to kind of clear the environment. Another way to clear the environment, if you want to just do it quickly, is you can type in the command rm list equals ls. List equals ls, and that will clear your environment as well. Okay, rm is the command used to delete things from the environment. List equals ls basically gives it a list of all of the ls, lists off everything that currently exists in the environment. This is basically remove all of that stuff. All right. This is a common issue students come and encounter, right? My code runs in R, but when I try to knit, I keep getting errors, right? So, you know, when you do your homework, one of the requirements for submitting your homework is that it's got to knit. You got to knit it to a PDF, and you were going to submit the knitted PDF, right? Don't submit your RMD file, okay? You're not going to get points for that, right? So you got to knit to a PDF, and you got to submit that, okay? Separately, submit your RMD file to Brew and Learn, but what we grade is the knitted PDF. It's got to output. So what's going on, right? My code, it runs in R, but when I try to knit, I keep getting errors. Now, there could be hundreds of different reasons why this happens, okay? But one of the most common scenarios looks something like this, okay? Is that as you're coding, you create some kind of object, all right? You're coding, you create some kind of object, and then later on, you change the code or you delete that line of code that creates that object, right? So you've created this object X. Later on, you change the line of code that creates that line X, or you delete that line or something, okay? And so that object X still exists in the environment, but the code that produces that object X is not in your RMD file, okay? So as you continue to write code and as you continue to run it, it works fine, okay? In R, it seems to work fine because that object X has been created and it exists in your environment, okay? But then when it comes time to knit, when R knits, it starts off with an empty environment, okay? It always starts off with an empty environment, and it runs your code line by line, and basically it encounters this line that says, okay, now take object X and do this thing. And because it started off with an empty environment, that object X doesn't exist in the environment, or exists in a different form where it's not compatible with this line of code. And then so now it runs into an error where it can't run this line of code, okay? So clearing the environment will help you debug this problem, okay? When you clear the environment, okay, now you start off with an empty environment, and you're going to run your code line by line, and you will encounter probably the same issue as you run it line by line, okay? And you're going to say, hey, do this operation with object X, and then it encounters an error and says, hey, X doesn't exist, or X isn't compatible with this thing. And then you look at your code and you go, oh yeah, I remember now. I made a change to X right here, and for whatever reason, I didn't save it in the RMD file, and then you have to insert that line back into your RMD file. So that's a common thing that happens when you clear your environment and work through your code line by line. A lot of times you'll encounter the same issue that R encounters when it knits, because when R knits, it always starts off with an empty environment. Now, if you don't clear your environment, those objects still exist, and so it's going to feel like your code still runs, okay? Because it's interacting with the objects that do exist in the environment. But when R knits, it always starts off with an empty environment, okay? Now, why does R always start off with an empty environment rather than the environment that currently exists? Well, part of the philosophy of having R Markdown and the knitting and stuff like this is this idea of reproducibility. And the idea is that I can give you my file, and you open it on your computer, and you're able to run it, okay? And if you want to be able to run it, you're going to start off with an empty environment, right? Unless I explicitly save objects and also transport those objects to your computer as well, right? And so those things, if you do need to load up data, those need to be explicitly called. And so the idea with knitting is that it's always going to start off with an empty environment, so that if somebody wanted to reproduce your results, they can do it on their machine. Couple other tips is don't save your R data when you exit R. So you can do this if you have your laptops open. You can go to RStudio, go to Tools, go to Global Options, and you can in the workspace save workspace to R data on exit. I always have never, and then I always uncheck restore R data into workspace at startup, okay? And that way, whenever I start up R, I always start off with an empty environment, okay? I always start up with an empty environment. And that also helps avoid certain issues, because, certain variable names like X or results or I or whatever, these are, common variables that we always use. Sometimes as you're writing code, if you have these old values getting loaded up, right, as you're working with them, it might reference these old values, and your code might run a little bit funny or wonky or something like that. Okay, so if you do have results that you do want to save, okay, you can always create some object. X is the integer 1 through 10, and you want to save that. You can always just save your workspace. You can always click the save button, save your workspace. You can always load a workspace, so that's fine. But it should be done it should be something that you do explicitly and manually yourself, rather than it loading automatically or unloading. Okay. A couple other things: toggle comments in your code. You can always kind of take lines of code, highlight them, Command-Shift-C or Control-Shift-C, and it will toggle this entire chunk, whatever highlighted lines, into comments or not. And so writing lines of code and commenting them is a common kind of debugging technique, where it's like, okay, if I have this line, what does it do? If I comment it out, what effect does that have? So that's a common thing that we want to do. You can also create new script files. You can hit Command-Shift-N. You can always just go to File right here under the new thing. You can create a new R script, or File, New File, and create a new R script and stuff, new R Markdown object, things like that. As you run your lines of code, okay, you can highlight a line and hit Command-Enter, or you don't even have to highlight it, so you can highlight the line and hit Command-Enter and it will run it, okay? Or you can just hit Command-Enter and it automatically goes to the next line. Or if you just want to run the entire code chunk, you can hit the little play button. Okay, the little play button will run the current code chunk. Okay, this little button next to it says Run All Chunks Above. Okay, and then here are different options and stuff. Okay, but here this I also frequently use this button, Run Current Chunk, and then go to the next line, run that current chunk, or you can hit this button, Run All Chunks Above, so on and so forth. And if you have an entire script that you've written, you can just hit Command or Control Shift S to do that. Okay. Other useful things is as you work, your console will fill up. You can hit Control L to clear that out. And you can restart your R session, and there's also a keyboard shortcut for knitting your RMD file. All right, let me go ahead and give you your first view quiz answer. It is the letter A as in apple, A as in apple. A as in apple is your first view quiz answer. Okay, let's talk about data structures, basic data structures in R. This, I imagine, is going to be review for most of you who've taken Stats 20, which is all of you. But it's good to kind of just review a lot of this stuff. Some of you took Stats 20 last quarter, and some of you took Stats 20 like a year and a half ago. So it's good to spend a little bit of time, and let's take a look. Okay, we got two types of vectors: atomic vectors, generic vectors. We might call generic vectors lists. And what is the main difference between an atomic vector and a list? You can think of your answer in your head. And the key difference is that an atomic vector, all of the values inside the atomic vector must be of the same type. Okay, so you can't mix different types in an atomic vector, whereas a list or generic vector, you can mix types. Okay, there are 6 basic types for atomic vectors. We've got the logical, the double, the integer, character, complex, and raw. We don't really interact with complex and raw too much in our day-to-day, but they do exist, and certainly they have their function. But most of the time, as far as as far as atomic vectors go, we'll just be working with the logical, double, integer, and character. Double is for anything with decimals, okay? Or that's just your generic numeric type. Floating point numbers, we'll talk about specifics of floating point numbers later on in the course, okay? Integers, obviously just whole number values, positive, negative, and 0. The mode of both logical, integer and double are numeric, and then the rest are the same as their type of. Okay. R automatically kind of converts between integers and doubles, and so you often don't have to worry about this. This is in contrast to other languages like C. C is like strongly typed, and you have to explicitly say, here's going to be this bucket that's going to hold an integer, and if you try to put a floating point number into that integer, it's going to either truncate that number or error out, or different things, right? It has a little bit unexpected value behavior. I mean, well, I guess it's understandable, and you can expect and predict its behavior, but it's different than like just working on plain old paper math, right? But even like floating point numbers also work different from plain old paper math, and we'll talk about that in like week 6. So yeah, doubles are numeric values stored with floating point precision. Why do we call it double? There is something called single precision floating point, which has kind of fallen out of favor just because we have so much memory on computers, right? Like your computer probably has 4 gigabytes, 8 gigabytes or more of RAM. So this is, back when, it was a luxury to have like 4 megabytes of RAM, storing your numbers was of more concern, and so you'd save space by using single precision floating point stuff. But now today we just use double for everything. Anyway, in R, if you want to have integers, you can put an L after it. Otherwise, by default, it's going to be double. So if I create a vector using C123, that's going to be type double. If you use a colon, it produces integers, okay? The number 1, is that double? Yes. 1L, is that integer? Yes. Okay, so we have these functions that will give you true, false, tell you what type it is. Lists are generic vectors. These allow you to have different types, okay, different types of values. And they are very flexible. You can put any kind of object inside a list, including functions and other lists and stuff like that. And here's like a little table that summarizes kind of these different data structures. So if everything's of the same type, data type, and it's one-dimensional, that is an atomic vector. If it's same data type and you have 2 dimensions, then that's a matrix. And if you got more than 2 dimensions, that's an array. If you have a one-dimensional thing and you want to be able to store different types, heterogeneous, then that will be a list. If you have different types in a 2-dimensional structure, that's a data frame. And we don't have anything that allows for higher dimensions with different data types. I guess just a bunch of different lists. Every kind of vector or whatever, you can attach something called attributes. Okay, it's optional for some of these things. Other things will kind of always contain attributes. Attributes are just a list of arbitrary values. There are kind of 2 attributes that are particularly important: the dimension attribute and the class attribute. Dimension attributes are used to kind of turn vectors, atomic vectors, into matrices and stuff. Class is the class attribute, powers our object-oriented system S3, and that we will cover in a couple of weeks here. Okay. Here's some questions that you can answer when you review these slides on your own time as you study. So the way we interact with attributes, we have 2 functions. ATTR is the function that we use to set attributes or get specific attributes. And if you just want to get all of the attributes associated with an object, you use the attributes function, okay? And you can think of attributes as basically like a sheet of paper that gets stapled on to the original object, okay? So the original object might be a vector, and you can just staple on a little sheet of paper that has additional information, okay? Or in this case here we have the original object is a list, and we staple on some information that makes it a data frame. And so here we have this data frame called trees, and I guess we have information about trees: the girth of the tree, the height of the tree, the volume of the tree. I don't know who collects information about trees like this, but whatever. And I should learn more about this data set, because 10.3, I don't even know what units are being used. Right? Is the girth of 8.3 big? I don't know. Okay, but we're talking about trees here, and if you say, hey, what are the attributes associated with the trees? Okay, this object called trees, it's basically a little sheet of paper, all right? And it says, oh, you know what? The column head names are girth, height, and volume. Okay, this is an object of class data frame, and data frames also come with an attribute called row names. And it says we have 31 row names, and they're the numbers 1 through 31, which seems a little bit silly, but yeah, you can have different names for the rows here, okay? And that's what we have. Now, if we wanted to, again, it's just a little sheet of paper. So if you wanted to add some extra information, you know, you could draw a little, not draw a picture, but you can just add something that you want, right? So here I'm going to just say, hey, I'm going to add a little piece, something called info, and I'm just writing a little sentence that says this data frame is about trees, and we're just adding that to this little piece of paper, okay? And so now I say, hey, what's on that attributes sheet of paper, okay? Now it contains this extra line that says this data frame is about trees. Now this is non-standard. This is not something we would normally do, but again, it's just an extra list where you can just attach extra things there if you wanted to, so it's possible. But yeah, this is not something we would normally do. And so the attributes power like our work with matrices, okay? Because internally, a matrix is just an atomic vector. So here I'm creating an atomic vector. It's just the integers 1 through 10. So I'm just saying M is a vector 1 through 10. And we can see that M is the vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I say, hey, what kind of thing is this? And I say class M, and it says it's just an integer vector. okay? Now I say, oh, wait, here's this atomic vector, and let me attach some attributes, okay? As I'm gonna just attach this piece of paper, and on this piece of paper I just write, we're gonna have dimension attribute 2 by 5, okay? So now it says, okay, here's this vector 1 through 10, but you know what? R, I want you to treat this as if it's a 2 by 5. It has dimensions 2 by 5, okay? And when we do that, now R says, oh, I've got to treat this like a matrix, okay? And it arranges the values in a rectangle, okay, with 2 rows and 5 columns, okay? So just this one little attribute that says dimensions 2 by 5 turns the one-dimensional vector into a 2-dimensional matrix. And so if I say, hey, what are the attributes of M? There's just one piece of information and it just says dimensions 2 by 5, okay? Okay, and now when we ask what is the class of M, okay, R understands and says, oh, well, we've got dimensions 2 by 5. This means this is a matrix, okay? And a matrix is basically a special case of the array. Okay, array is just anything that's an atomic vector with dimension attributes to it, and a matrix just says, hey, we only have two dimensions, rows and columns. Okay. Now, if I wanted to, if I remove that piece of paper, if I threw it away, right? So I'm going to say dimensions null. Okay, we're going to just take away this dimension attribute. Now, R says, oh, now we're just back to a vector, 1 through 10. And so if I remove the dimension attributes and I just say, hey, what's M? M is just back to integer vector, 1 through 10. Class of M is now integer. So just that little kind of just attaching that little sticky note that says, hey, dimensions 2 by 5 is going to turn something from an atomic vector into a matrix and back. Okay, array is the same kind of thing. It's just rather than having just how many rows and how many columns, you have a third dimension, so you can have rows and columns and layers. All right, and so now we have a 3-dimensional array. So we have 2 rows, 3 columns, 2 layers. So first layer is 1, 2, 3, 4, 5, 6. Second layer is 7, 8, 9, 10, 11, 12. Okay, and that's done by this. And you can also create arrays using array, but that's how that works. Let me go ahead and give you your second view quiz answer is the letter B. B as in bear. B as in bear is your second view quiz answer, B. Okay, internally, the way R stores a data frame is it is a list. Okay, internally it's a list, and the list, it contains vectors, atomic vectors of equal length. So again, I have this data frame called trees, and if I say, hey, what's inside? It is a list, and there's three things in the list. There is a vector of girth measurements, a vector of height measurements, a vector of volume measurements. Okay, and internally we say, hey, what's the class of this list? And we have the attributes that says it's a data frame. And when R sees that it's a data frame, then it treats it a little bit different from a regular old list, and it says, okay, when you want me to show you the data frame, I know to arrange it into this table form. Okay, but yeah, internally, if we say what's the type of, it's a list. It's a list. Okay, we also have factors. Factors are vectors that are used to represent categorical values. Okay, internally, a factor is stored as an integer vector, right? So internally we store factors as integer vectors, and we also have these attributes for levels and class, okay? So here we have the gender is, I create a character vector, okay? So this is originally character vector, and I have the characters M, F, F, X, M, and F. And then I'm going to convert the character vector into a factor, okay? And so I say factor wrapped around the character vector, and so now we have gender factor. And so now I have the factor, and it says M, F, F, X, M, F, and the levels F, M, and X. And we can say, hey, what are the levels on this gender factor? And it says you've got 3 levels, f, m, and x, and the type of, internally it's stored as an integer. There are things to be careful with. So again, factors are used for categorical values, and internally they're stored as integers. Okay, so internally, if we look at the gender factor, and I say, hey, what are the what if I turn this back into an integer, because internally it's stored as integers, right? Internally, it's stored as 2, 1, 1, 3, 2, 1. Okay, 2, 1, 1, 3, 2, 1, right? And R just knows anytime it sees a 2, it means M. Anytime it sees a 1, it's an F. Anytime it sees a 3, it's an X, right? So the M gets stored as a 2, the F is a 1, F is a 1, X is a 3, M is a 2, F is a 1. And so internally it's stored as 2, 1, 1, 3, 2, 1, and then R just knows to, when it represents these things, to replace the 1s with Fs, the 2s with Ms, and the 3s with Xs, okay? And that's what we have. Now, sometimes you have numbers that, variable that looks like numbers, but they're really categorical things, right? So, for example, your phone number area code, okay? It's a number, but it's not a numeric quantity. If we kept information about all the students, and one of the things is what's your area code or what's your zip code, that would be a categorical variable, okay? And it's categorical because it doesn't make sense to do numeric comparisons, right? Something like age, it makes sense to say this person's 22, this person's 20, this person is 2 years older than the other person, okay? You take height, this person is 5 inches taller than someone else. This person's weight, this person is 10 pounds less than someone else's weight, okay? You can do numeric comparisons if it's numeric. When it's categorical, the numeric comparisons don't make sense. It does not make sense to say, oh, your area code is 818, your area code is 310, you have 508 more area code, right? Okay, and it doesn't make sense to say, hey, what's the average area code, right? The average area code is 43.7, okay, or 433.7. That doesn't make sense, right? The average area code doesn't make sense, something like that, or the mean of the area code. So those things don't make sense. Sometimes, you're recording information, and this is, you say this is category 1, and this is category 2 or category 3, and you're writing down numbers 1, 2, and 3, but they actually represent something else, right? Category 1 could be, I don't know, the vehicle comes from North America, and category 2 could be vehicle comes from Europe, and category 3 could be vehicle comes from Asia or something like that. These are not, they don't have numeric meanings, right? It doesn't make sense to do like an average, okay, of these values. Okay, so let's say we have this variable, and it has the values 0, 1, 10, and 5, and these, this is categorical. It's a factor, all right? So internally it gets stored, so we have 0, 1, 10, and 5. Internally it's an integer vector, and if we say, hey, what's the mean? Okay, what's the mean? R is going to start off and say, this is a factor. I don't think you want to do this, right? It's not numeric, it's not logical, so it's going to return an NA. Now you could twist R's arm and you could say, hey, make it numeric, and then give me the factor, all right? And if you do that, it says, okay, and it gives you a 2.5. Now, the numbers, though, are 0, 1, 10, and 5, right? 0, 1, 10, 5, that adds up to 16. 16 divided by 4 is 4. The mean of 0, 1, 10, and 5 should be 4, but it's giving me back a mean of 2.5. So what's going on? Well, internally, when you say as numeric for the factor, the 0 gets stored as a 1, the 1 gets stored as a 2, the 10 gets stored as a 4, and the 5 gets stored as a 3. So internally, it's 1, 2, 4, and 3, and then when we say what's the mean of that, the mean of that is 2.5, okay? But that's probably not what you wanted. If you wanted to treat this like numbers and take the average, then you have to take a couple more steps. One is you have to convert the factor into character. So you'll get the character 0, character 1, character 10, character 5. Then convert the characters to numbers to get the numbers 0, 1, 10, 5. And then you can take the mean. And then you'll get the number 4. But if that's what's going on, you probably should ask yourself, should this really be stored as a factor? Okay? Because if you're able to take the mean of something and it makes sense, then it's going to be a numeric variable. Okay? And if it's stored as a factor, you have to kind of ask, does it make sense to take the mean, right? When you have factors, you can't enter values that are not part of the levels. So in our gender factor, the levels that we had are F, M, and X. And so if you try to store the value character male in here, it says, nope, can't do that, NA generated, and you get a warning, okay? So that's how factors work. And you got a couple questions or a question in the homework going into the details of factors as well. Coercion. Coercion is the thing that happens when you combine different vectors of different types. Okay, so again, one of the rules for atomic vectors is that everything in the vector has to be of the same type. So here I have 4 different atomic vectors. The first one is L, logical vector. It contains the values true and false. I have an I, which is an integer vector, and it just contains one value, the integer 1. D is double, 5, 6, and 7, and CH is character, letters A and B. And what I'm going to do is I'm going to combine the logical, the integer, and the double. I'll also combine the logical, the double, and the character. And what are the types here? Okay, and you can check this as you quiz yourself. When we combine the logical, the integer, and the double, the R, what it does is it looks to what is the least restrictive of the types. And the most restrictive is logical, and then next most restrictive is integer, next is double, then we have character, and then list is the least restrictive. And so it's going to say doubles are the least restrictive of L, logical, integer, and double. So it's going to coerce everything into double. So the logical vector, which is true and false, gets coerced into doubles. So the true become a 1, the integer, the false becomes 0, integer remains 1, doubles remain 5, 6, 7, and so we get 1, 0, 1, 5, 6, 7. When I do L, I, and CH for logical, integer, and character, character is the least restrictive type. So it's going to convert the logical into character, and so now we get true in quotes, false in quotes. Integer is 1 in quotes, and then we have A and B, and that's what we have there. So when we combine them, we get different results depending on what got combined. Coercion happens implicitly when you call any kind of function. So basically any kind of mathematical function, like a plus sign, multiplication, log, absolute value, etc. Or you use any kind of, we'll convert things to double or integer. And then logical operations, anytime you use an and sign, an or, an any, or whatever, we'll coerce it to logical. So here I've got this logical vector containing the values false, false, and true. Now if I said make that numeric, it would turn it into 0, 0, and 1. Here I could take that original logical vector, false, false, true, and say, hey, what is the sum? Okay, and again, implicitly, it converts it to 0, 0, 1, and the sum of 0, 0, 1 is 1. I could say, what's the mean? And it's going to do 0, 0, 1, and what's the mean of 0, 0, 1? It's going to get 0.33. And so this is a handy thing because sometimes you just want to get what's the proportion of some values, and this will do it, okay? So if you have a data frame, you can do some kind of logical thing. You can say, hey, what proportion of people are from California in my data? And then so you just do state equals CA, and you'll get a bunch of true, false values, and then you can say, what's the mean of that? And that will give you the proportion of trues. You'll get the proportion of people in your data that are from California. Handy thing, okay? If I did as character on that logical vector, now we get the false, false, true, but in quotes. Values like 0 and 1, and when we say coerce them to logical, 0 becomes false, 1 becomes true. If you ask it to do something that R is just not able to do, say like take the word dog and make it numeric, R is going to come back and say, I couldn't do it, right? It says, warning, NA is introduced by coercion. Any kind of numeric value that when you say make it logical, zeros become false, every other numeric value becomes true. And then nan, which is also a numeric value, becomes NA. So 0 becomes false, 1 becomes true, -1 becomes true, 0.1 becomes true, 2 becomes true, negative infinity becomes true, 2.2 times 10 to the negative 308, which is one of the smallest possible values that we could possibly represent in floating point system, that also becomes true. Okay, only 0 becomes false. Okay, and so this is a thing. Sometimes in like floating point math, you'll get a value that's close to 0 but not exactly 0. Okay, and if you say, hey, make that into a logical thing, it's going to come back true, even though you're like internally in your brain you're thinking it's 0, right? So if you say like, I don't know. Okay, so and then you got nans become NA. If you have things and you want to turn them into logical values, these are the accepted spellings for false and the accepted spellings for true. So capital F becomes false, capital T becomes true. But if you tried to convert something like this, lowercase f is going to become NA, lowercase t is going to become NA. Okay. Other words, other things will become NA. Cat will become NA. What happened here? Why did the 0 and 1 become NA? Right? Over here, the 0 and 1 became false and true. But why did the 0 and 1 become NA here? Okay. Yeah, the coercion, right? So the first thing that happened is when we combined the 0 and 1 using the function c, it coerced the 0 and 1 into character 0 and character 1, okay? And character 0 becomes NA and character 1 becomes NA, okay? Whereas the numeric values 0 and 1 will become false and true. Okay, what's the difference between NA, null, and nan? You don't have to answer this. I'll answer it for you, but this is a good question to ask yourself later. NA is used to represent missing or unknown values. We have an NA for each data type. This is something unique to R, and this is one of the reasons why I think R is so well suited for handling data and working with data, is that missing data is a very common thing, and R has a way to handle missing data that I think is fairly unique, okay? Null is used to represent values that do not exist, non-existent values, and null is its own type, okay? And then we also have nan. Nan is a double type, and it's used to represent kind of indeterminate mathematical forms, like 0 divided by 0, or infinity minus infinity. Those result in nan, and that differentiates R from other languages, say like Python, where Python, basically anything missing is represented with a nan, and you can't have missing integers. Integers have to be coerced into or upcast into floating point if you want to have any kind of missing values there. I love Python, and I also teach courses in Python, but R this is something that R does that I really like. Okay, so an example of when we use NA and when we use nan is, let's say you're storing information about people, and you've got a column to store the person's name, person's age, their partner's name, their partner's age, maybe other columns and stuff, right? And so let's say you're storing information about Joe, okay? So you have Joe under the name. You don't know Joe's age, all right? So you put an NA for Joe's age, okay? Because we know Joe has an age, we just don't know it, okay? On the other hand, Joe does not have a partner, okay? So as far as the partner's name, we put in null, okay? And we're also going to put in null for the partner's age. These are values that do not exist at this moment in time, okay? Now, if Joe did have a partner and you just didn't know what that partner's age is, then you would use NA instead, because this thing exists, but we just don't know it, all right? So that's the difference between NA and null. Okay, NA, we have an NA for each type, and so when you insert an NA, it's not going to change it. So internally, we have NA which is the type logical. NA integer for integer, NA real. I don't know why we don't call it NA double, but it's NA real. And then we have NA character. You also have, you know, other NA types. But basically, you can insert an NA, and it's not going to change the type. Now, if you want to check if something is missing, you have to use is.na, is.na, to see if it's missing. Now, if you do NA equals NA, we're basically saying, okay, there's a value inside this bag, and we don't know what it is. And over here, there's a value inside this bag, and we don't know what it is. Is the value inside this bag equal to the value in this bag? That's what the first question is asking. And the answer is going to be, well, I don't know. I don't know what the value is. So the answer is I don't know. And that's why you get an NA. Okay? Whereas we just say, hey, is the value in this bag unknown? And you go, yeah, the value in this bag is unknown, right? Versus like, oh, here's a clear bag, and we can know what the value is inside. Then we'd say, oh, it's not missing. Okay? Null, on the other hand, is null. Type of null is its own type. It's null type. And if you want to see if something is null, you're going to use is null. If you ask if the null is missing, it's not. Null is just nothing. It doesn't exist. So we say, is the thing here an unknown value? And the answer is like, it's not even a value in the first place. Okay. So the answer is neither yes nor no. It's just, so we get a logical length 0. Okay. The is.na says, okay, my answer is going to be true or false, but I don't even have anything to answer with. So you're going to get a length 0 answer, okay? Length 0 answer is what integer, logical 0 is saying, okay? Is null a logical value? It's not. It's its own type, okay? And anytime you try to do operations with null, it's like you don't have anything, right? So you're saying, okay, add something to nothing. Okay, add false. The plus false coerces this to an integer 0. So well, we're doing nothing plus 0, and you're like, I can't add something to this thing, right? So we get integer of length 0. If you try to insert null into a vector, it's like including nothing. So I have 4, 5, null, and 3. That's just, this is a length 3 vector. This is not length 4, it's length 3, okay? And then you can't compare nothing with nothing, okay? That just doesn't work. Let me give you your last view quiz answer. Last view quiz answer today is the letter E. E as in elephant. E as in elephant. All right, and I might go 1 minute over here, and I ask for your forgiveness there. Okay. Vectorized arithmetic in R. So R, when it does operations, it is vectorized. So I've got 1, 2, 3 is x, y is 100, 200, 300, and when you do x plus y, it's going to do 1 plus 100, 2 plus 200, 3 plus 300, okay? When you do the multiplication, 1 times 100, 2 times 200 is 400, 3 times 300 is 900, okay? R recycles. So when I do 1, 2, 3 plus 100, 200, 300, 400, 500, 600, it's going to do 1 plus 100, 2 plus 200, 3 plus 300, then it recycles the 1, 2, 3, and it's going to do 1 plus 400, 2 plus 500, 3 plus 600, okay? It does the same thing down here, but it complains, right? So up here, it did that 1 plus 100, 4 plus 400 plus 1, 500 plus 2, 600 plus 3. Here, we get the same results, but then it says, hey, you know what? I went 1, 2, 3, 1, 2, and then I have a 3 left over, so I'm not sure if this is what you wanted me to do, and it complains with a warning. Okay, same kind of thing with matrices. Here I have a matrix, and I've got a vector 100, 200, 300. But one thing about the way R handles recycling with a matrix is it does the vectorized operations vertically. Okay, so it's going to do 100 plus 1, 200 plus 4, 300 plus 7, then 100 plus 10, 200 plus 2, 300 plus 5. And you're going to get this. And it's not going to complain because everything lines up. But this is probably not what you wanted it to do. I imagine in this case you might have wanted 100, 200, 300, 100, 200, 300 across the rows. So if you want to do something like that, you have to be a little bit creative, and you would transpose this matrix so that the rows become columns. Then you could add that operation, 100, 200, 300, and it does it vertically. And then you transpose it back. So now the 100, 200, 300 gets added across the rows. Okay, that is it for today. Have a great rest of your day. I have office hours at 11:30, and we will see you on Friday.